Imagine a world where time slows down, space bends, and energy transforms into mass. Welcome to the universe of Albert Einstein. Now let's dive into the life of this extraordinary man. Born in Germany, Einstein's early years were marked by a rebellious nature and a deep-seated curiosity that traditional education failed to satisfy. He was a boy who preferred compasses over toys and daydreams over directives. Fast forward to his 20s. Einstein found himself in the unlikely role of a patent clerk in Switzerland, but don't be fooled by the mundane title. As he sifted through patents by day, his mind was busy wrestling with the fundamental laws of nature by night. This intellectual tug-of-war would ultimately lead him to formulate theories that would forever alter our understanding of the universe. A humble patent clerk by day, Einstein was a ferocious beast of thought by night, destined to unravel the mysteries of the universe. In 1905, Einstein shocked the world with his groundbreaking theory of relativity. This theory, known to many as the special theory of relativity, is hinged on two fundamental principles. First, that the laws of physics are the same for all observers, regardless of their state of motion. Second, that the speed of light in a vacuum is constant for all observers, irrespective of their state of motion or the motion of the source of light. Now let's delve into the first principle. It implies that whether you are sitting still in your living room or hurtling through space in a rocket, the way you observe the laws of physics will be the same. A ball thrown up in the air will always come down, whether you're on a moving train or standing still. This is a concept that is quite intuitive and aligns with our everyday experiences. The second principle, however, is where things get interesting. It states that the speed of light is always the same, roughly 300,000 kilometers per second, no matter how fast you are moving towards or away from it. This might seem counterintuitive to our everyday experiences. For example, if you were to throw a ball while running, the ball's speed would be the speed of your throw plus your running speed. But light doesn't play by these rules. These principles have profound implications. They lead to concepts such as time dilation and length contraction. Time dilation tells us that time can slow down or speed up depending on how fast you are moving or how strong the gravitational field around you is. Length contraction, on the other hand, suggests that objects can appear shorter in the direction of motion as their speed approaches the speed of light. Einstein's special theory of relativity not only redefined our understanding of space and time, but also set the stage for his most famous equation. This theory was a revolutionary step that forever altered the course of physics, setting us on a path to discover the intriguing and often mind-boggling realities of our universe. mc², a simple equation etched in the annals of science, forever linking energy to mass. This equation, though it looks straightforward, sent shockwaves through the scientific world. Let's break it down. E stands for energy, m for mass, and c is the speed of light, a constant. The equation tells us that energy and mass are interchangeable. They're different forms of the same thing. This revelation was groundbreaking, to say the least. It means that a tiny amount of mass can be converted into a tremendous amount of energy. This principle is at the heart of nuclear energy, where small amounts of matter are transformed into large amounts of energy. On a darker note, it also paved the way for the development of atomic weapons, demonstrating the immense power, but also the potential peril, of this scientific breakthrough. With mc², Einstein had rewritten the rules of the universe, but his intellectual journey was far from over. In 1915, Einstein unveiled his general theory of relativity, a theory that predicted the existence of black holes. But what does this mean? Well, the general theory of relativity is a bit like a grand cosmic dance. It tells us that massive objects like planets and stars distort the fabric of spacetime around them, sort of like a bowling ball on a trampoline. This curvature of spacetime guides the paths of smaller objects, creating what we perceive as gravity. Now imagine an object so massive, so incredibly dense, that it warps spacetime to the point of no return, a black hole. These cosmic anomalies were a direct prediction of Einstein's theory. They are regions where gravity is so strong, nothing, not even light itself, can escape their pull. Einstein's theories continue to shape our understanding of the cosmos, proving that the universe, like the mind of its discoverer, is wonderfully strange and endlessly fascinating.